In the previous sessions, we were discussing some consequences of the completeness axiom that are satisfies. We are continuing with the discussion and we are going to have a few more serious results concerning the completeness axiom. And the very first one that we are going to discuss is a result known as nested interval property. Nested interval property in R states the following. For each natural number n, assume that we are given a closed interval named by in, which is equal to the set of all x in R such that x lies between an and bn. Also assume that this interval in, the sequence of the interval in, that is nested. So nested means that in contains in plus 1 for each n. That means that I1 contains I2, I2 contains I3, etc. Then the resulting nested sequence of closed intervals nested sequence of closed intervals means uh, the sequences, the closed intervals in this form, I1 contains, I2 contains, I3 contains, etc. has a non-empty intersection. That is intersection n, the infinite intersection in is not empty. So, what exactly nested interval property says is the following. Suppose that corresponding to each natural number, we consider a closed interval in, and this in satisfy the property that ins are nested, in the sense that I1 contains, I2 contains, I3, etc. like that. So, if you have a sequence of intervals like this, then the nested interval property says that the intersection of all these intervals taken together, that is intersection n equal to 1 to infinity in, that will contain at least one element. That is, it is not empty. So we have to consider closed interval satisfying this property, and we have to find out at least one element in the intersection. That is what we have to prove. So the intervals are going to look like somewhat this. We have somewhere here an, and somewhere here, sorry, not an. This is starting with a1, and here we have correspondingly b1, and a2 is appearing somewhere here, and b2 maybe somewhere here, and a3. A3 can be equal to a2. There is no problem. A3 is also, suppose it's here, and b3 is somewhere here, and we are continuing like this. AK is here, correspondingly some BK is here. We are considering intervals in this form. So here we have elements of the form A1, A2, etc. Here we have elements of the form here we have A1, A2, etc. Here we have this is starting from here B1, B2, etc. going up to BK, etc. AK. Okay. These are the intervals we are having, and these are the endpoints. A1, A2, etc. are the left endpoints of the closed intervals, and B1, B2, etc. are the right endpoints of the closed interval. Now, we are going to use the axiom of completeness that is satisfied by R to establish that the intersection actually contains at least one real number. For that, we are going to consider to use axiom of completeness. We need to actually find out a set that is bounded above. To construct such a set, we will consider the left endpoints of all these closed intervals and call that set to be A. So A equal to the set of all left endpoints of all these intervals. That is an. N belongs to n, and an are left endpoints of in. Therefore, A is nothing but it's equal to A1, A2, etc. Now, we can see that A1 is the left endpoint of the interval I1 and the right endpoint is B1. Therefore, A1 is less than or equal to B1 since I1 we have is equal to A1 B1. This is not worse. Sorry, this is not IN, it's I1. This is not worse. Now, what is the property of A2? So A2 belongs to I2 equal to A2 B2. This is the left end point of I2. But remember that A2, the set A2 B2, if you consider this set A2 B2, the interval that is actually inside I1 equal to A1 B1. So the structure of A1 B1 and A2 B2 is something like this. We have A1 B1, A2 B2. We have A2 here, B2 here. So what you can say about A2 now? We can say that since A2 B2 is inside A1 B1, A2 is going to be less than or equal to B2, but at the same time B2 is less than or equal to B1. So the sequence of endpoints actually satisfy this property. A1, just look at the picture here. A1 is going to be less than A2, is going to be less than or equal to A1, going to be less than or equal to A2, going to be less than or equal to A3, etc. So A1 less than or equal to A2, less than or equal to A3. It goes on like that, less than or equal to AK, less than or equal to etc. Now, what about B1, B2? B1, we know that. Look at this picture once again. B1 greater than or equal to B2, it's the other way. B1 greater than or equal to B2, greater than or equal to B3, greater than or equal to etc., greater than or equal to BK, greater than or equal to etc. Now, how do we compare these AIs and BIs? Of course, we know that A1 is less than or equal to B1, and you know that A2 is less than or equal to B2, A3 is less than or equal to B3. That's quite clear to us. Now, can we say that? Can we say that AI is less than or equal to BJ for every IJ? That's the question. See, if we look at this figure, that actually becomes somewhat obvious. See that A1 is lying to the left of B1, A2 is lying to the left of B1, A3 to the left of B1, A3 is here and B1 is here. And not only that, since these intervals are all nested in the sense that suppose that we have the interval I1 here, this is interval I1, this is A1, this is B1. After that, we are going to have I2 here, I2, this is A2, this is B2. After that, we have A3, B3. Just if we look at all these things, we can see that A1 is less than A2, A1 is less than equal to A2, A2 is less than equal to A3, but now A3 is less than equal to B3. Therefore, A1 is less than equal to B3. Now, A2 is less than equal to B2, but B2 is less than equal to B1. Therefore, A1 is less than equal to. See, we are getting every AI to be less than equal to every BJ. We will try to see this using some simple example. And the general case also can be verified exactly like that. So suppose that we want to see, for example, uh, can we say A3 less than or equal to B5? That is the first question. Okay, now how do we put these things? A3 less than or equal to, here we have A1, we have A2, A3, and on the right side we have B1, B2, B3, B4, B5. From this picture, it's actually very obvious that A3 is less than or equal to B5, but we have to see it using some other way. A3 less than or equal to B5 is what we want to see. Now, but to see this, just observe that A1 less than or equal to A2 less than or equal to A3 less than or equal to A4 less than or equal to A5. Now, A5 B5 is nothing but this is equal to I5. Therefore, A5 is less than or equal to B5. So these together will give A5 less than or equal to B5 and A3 is less than or equal to A5. So A3 less than or equal to A5 less than or equal to B5 or A3 less than or equal to B5. So that we establish. Next thing is probably what about is A3 less than or equal to B2. See here, we are looking at AI we are taking, and in the previous case we have taken one BJ in such a way that J is greater than or equal to I. Now we are taking the other way. Is A3 less than or equal to B2? That is the next question we have. So again, looking at this picture, we have A1, A2, A3. Now here B1, B2. Now we want to see if A3 is less than or equal to B2. Now see that A3 is the left endpoint of I3 equal to A3 B3. Now by what we have seen here, B3 is less than or equal to B2. B3 is less than or equal to B2. Now A3 is less than or equal to B3. B3 is less than or equal to B2. Therefore, A3 less than or equal to B2. So the conclusion is the following. In either of the cases, if I greater than or equal to J, then AI is less than or equal to BJ. If I less than J, then A is greater than less than or equal to Pj. In whatever case we are choosing, there are only two cases. I is greater than or equal to J or I is less than J. In whatever case we are choosing, we are getting AI to be less than or equal to Bj. See this example. In the first case, we have taken A3 less than or equal to B5. Here I is 3 and J is 5. So I is greater than or equal to 5. I is greater than or equal to 5. That is the first case. Then in that case, we establish that A3 is less than or equal to B5. In the second case, we have taken A3 and B2. So I is now greater than or equal to, see, in the previous case, we have um, 3 and 5, and the case I is less than or equal to J. I is less than or equal to J is the second case. I is less than J is the second case. And in the second case, we have 3 and 2, that is I greater than or equal to J case. In that case also, we have A less than BJ. Therefore, in both these cases, this is true. So, what is the final conclusion? We have A is equal to A1, A2, etc. For this set capital A, we have seen that whatever AI we are choosing, that is going to be less than or equal to Bj for every j. A has BI as upper bounds. So B1 is an upper bound of these AIs, B2 is an upper bound of these AIs, etc. Every BJ for J equal to 1, 2, etc. So the final statement we want to make is that the set A is bounded above. We have several bounds, therefore A is bounded above. Now the completeness axiom is going to be used here. A is a bounded set, it's bounded above, not necessarily bounded. A is bounded above. Not only that, A is non-empty because A1 belongs to A, A2 belongs to A, etc. We have infinitely many left endpoints, so this is non-empty. So by completeness axiom, what we can say, A has a supremum. Supremum of A exists in R, and write that supremum as X. So X is equal to supremum of A exists in R. That's what the completeness axiom guarantees. Now X is therefore X is an upper bound of A. Not only that, it is the least upper bound of A. What are the elements in capital A? Therefore, AI less than or equal to X for all I. So X is an upper bound of A, therefore AIs are going to be less than or equal to X for every I. Now, X is the supremum, therefore it is the least upper bound. What about B1, B2, etc.? They are all upper bounds of A. B, J are all upper bounds of A, and X is the least upper bound LUB supremum. Since X is LUB, X must be less than or equal to Bj for all J in N. So what are the two properties that this X satisfy? AI, here we probably put I itself. That's a I, I, I. So AI less than or equal to X less than or equal to Bi. That is, X belongs to I, all I equal to 1, 2, etc. That means X belongs to N, N here, N here, N here. X belongs to intersection N from 1 to infinity. So what we claim this intersection is not empty, and to prove that I intersection In is not empty, we constructed an element X belonging to all the Ins. Hence, the nested interval property is completely proved. Let us quickly go through the major components in the proof of nested interval property. So initially, we had a few closed and bounded intervals in the form In is equal to A and Bn, and these are all nested in the sense that I1 contains, I2 contains, I3 contains, etc. So from that, we assumed one condition on this, we actually understood one condition for the left endpoints, ANs. The condition was that A1 is less than or equal to A2, less than or equal to A3, less than or equal to etc. And after that, we have a condition on the right endpoints also. The condition on right endpoints is that the right endpoints are actually decreasing in the sense that B1 is greater than or equal to, B2 is greater than or equal to. So the next observation is the following, that each AI is less than or equal to every Bj. That's what we wanted. We are not actually saying that one A1 is less than or equal to B1, A2 is less than or equal to B2. That is of course true, but we are actually asking for something more stronger. What we are saying is A1 is less than or equal to B1, A1 is less than or equal to B2, A1 is less than or equal to B3, etc. And after that, A2 is less than or equal to B1, A2 is less than or equal to B2, A2 is less than or equal to B3, etc. That means whatever AI we choose, all these AIs are less than or equal to any of the BGs. That's what we wanted. So just satisfying that AI less than or equal to BI is not enough. We want AI less than or equal to BJ. So I and J can be completely different. So we observed that this is true in two examples. So in one example, we have taken the suffix of the index of A to B more than the index of B. That means I greater than or equal to J. And in the second example, we have taken I less than or equal to J. We observed that in both these cases, we are getting A to be less than or equal to BJ. And it is not very difficult to actually write down a proof for general I and J instead of using the examples. But we are not going into that part because geometrically also it's actually very obvious that A is less than or equal to BJ. So the next thing is the set of all AIs, the left endpoints, are now bounded by each and every BIs. Therefore, if we take the set of all left endpoints to be the set A, then we have the set A bounded above by B1, B2, B3, etc. by completeness axiom. Therefore, we have A has a supremum. We call that supremum to be X. That X is greater than or equal to all the AIs because it's a supremum of AIs. That X is less than or equal to all the BJs because BJs are all upper bounds for the set capital A and X is supremum, which is least upper bound. So X lies between AI and BI. A and BJ, and we can take A and BJ, A and BI also because they can be anything including I. So A is less than or equal to X less than or equal to BJ. Therefore, X belongs to interval I or interval IN. Since X belongs to each and every IN, we get that X belongs to the intersection of ions also, and we found an element in the intersection verifying the nested intervals property. Hence, we completely prove nested interval property.